In computer science, concurrency is the art of making computers juggle tasks simultaneously. It powers modern operating systems and applications, but demands careful orchestration to avoid chaos. Imagine a bustling city with cars, bicycles, and pedestrians. Without traffic signals, chaos would ensue. Similarly, concurrent programming requires synchronization to ensure processes share resources safely. Synchronization acts as the traffic signals of our digital cities, preventing errors and maintaining order. Without it, programs would face unpredictable issues. Two major pitfalls in concurrency are race conditions and deadlocks. Race conditions are like unpredictable car crashes, while deadlocks are traffic jams that bring everything to a halt. Understanding these challenges is crucial for writing reliable concurrent programs. Synchronization is the invisible hand that ensures smooth operation in the world of concurrency. Let's explore these concepts further to understand their importance. Welcome to the world of concurrency. Imagine two threads updating the same variable simultaneously. One thread reads, calculates, and prepares to write, while the other swoops in and overwrites it. This unpredictable timing creates a race condition, leading to subtle, hard-to-debug errors. Race conditions often manifest as intermittent bugs, failing under specific timing conditions. To prevent them, we enforce mutual exclusion, ensuring only one thread accesses a resource at a time. Think of it as a single-lane bridge where only one car can pass at a time. Synchronization mechanisms like semaphores and condition variables help achieve this. By understanding race conditions and mutual exclusion, we can write robust concurrent programs. These tools ensure processes cooperate without stepping on each other's toes. Race conditions are preventable with the right strategies. Let's dive deeper into synchronization techniques. The key to concurrency lies in mastering these challenges. Deadlocks occur when two threads hold resources the other needs, refusing to release them. It's a stalemate, like a traffic jam where no one can move. Deadlocks can cascade, affecting entire systems if not addressed. To avoid them, we need careful resource allocation and synchronization strategies. Techniques like resource ordering and deadlock prevention algorithms are essential. Think of traffic lights and roundabouts preventing gridlocks in a city. Similarly, these strategies ensure threads acquire resources in an order that avoids circular dependencies. Deadlocks are the ultimate concurrency challenge, but they're preventable. By understanding their causes and solutions, we can keep systems running smoothly. Deadlocks remind us of the importance of thoughtful design in concurrent programming. Let's explore how to prevent these crippling standstills. Concurrency thrives on avoiding deadlocks. Semaphores are the guardians of shared resources in concurrent programming. They act as traffic signals, directing processes to prevent chaos. A semaphore uses a counter to manage resource availability. When the counter is positive, resources are available. When zero, processes must wait. Semaphores enforce mutual exclusion, preventing race conditions. They ensure only one process accesses a critical section at a time. Binary semaphores and counting semaphores cater to different synchronization needs. These tools are essential for building robust concurrent systems. Semaphores bring order to the complexity of concurrency. By mastering them, we can create reliable and efficient programs. Let's delve into the types of semaphores and their applications. Semaphores are the foundation of synchronization. Binary semaphores operate with a simple on-off state, available or unavailable. They enforce mutual exclusion, ensuring only one process accesses a resource at a time. Imagine two threads updating a shared counter. Without synchronization, increments might be lost. Binary semaphores solve this by allowing only one thread to access the counter at a time. Once the thread finishes, it releases the semaphore for others to proceed. Despite their simplicity, binary semaphores are versatile and foundational. They prevent race conditions and maintain data integrity. Binary semaphores are the building blocks of synchronization. Let's explore their role in concurrent programming. Simplicity is their strength. Counting semaphores manage access to a finite pool of resources. Imagine a library with limited copies of a book. A counting semaphore tracks availability. Each wait operation decrements the counter, and each signal increments it. If no resources are available, processes wait in a queue. Counting semaphores are ideal for resource pooling, like thread or connection pools. They ensure processes don't exceed available capacity. By managing limited resources effectively, they prevent system overloads. Counting semaphores are flexible and efficient. They are crucial for scenarios involving shared resources. Let's see how they optimize resource management. Counting semaphores balance demand and availability. They are indispensable in concurrency. Semaphores power real-world systems, from databases to operating systems. In databases, they ensure data consistency during concurrent transactions. Semaphores prevent data corruption by allowing only one transaction to modify a record at a time. Operating systems rely on semaphores for process synchronization and resource management. They manage access to shared resources like printers and files. Semaphores also synchronize processes, ensuring smooth system operation. Beyond these, semaphores are used in networking and embedded systems. They manage buffers, communication channels, and hardware resources. Semaphores are fundamental to building robust and efficient systems. Their real-world applications highlight their importance. Let's explore how semaphores shape the systems we rely on. Semaphores are the unsung heroes of computing. Condition variables allow threads to wait for specific conditions to be met. Unlike semaphores, they work with mutexes and shared data structures. Threads waiting on a condition variable release the mutex and sleep until signaled. This avoids busy waiting, saving valuable CPU cycles. In a producer-consumer scenario, condition variables signal when data is available. They provide an efficient way to synchronize threads based on events. Condition variables add finesse to synchronization. Let's see how they complement semaphores in concurrency. They are the key to nuanced synchronization. Semaphores and condition variables serve distinct purposes in synchronization. Semaphores manage resource access, while condition variables wait for specific events. Semaphores are standalone, while condition variables work with mutexes. Signals in semaphores increment counters, while condition variables signal only waiting threads. Semaphores excel at resource management, condition variables at event-based synchronization. Choosing the right tool depends on the scenario. Both are essential for robust, concurrent programming. Understanding their differences is crucial for effective synchronization. Semaphores and condition variables complement each other. Together, they address diverse synchronization challenges. Let's explore their roles in building reliable systems. Synchronization thrives on the right tools. The true power of condition variables lies in their ability to signal events and notifications, allowing threads to synchronize their actions based on specific occurrences, rather than just resource availability. Imagine them as digital messengers, delivering important updates and waking up sleeping threads precisely when needed. One common use case is implementing thread-safe queues, where producer threads add data and consumer threads retrieve it. A condition variable can be used to signal consumer threads that data is available in the queue. When a producer thread adds data, it signals the condition variable, waking up a waiting consumer thread. Conversely, if the queue is empty, consumer threads can wait on the condition variable, releasing the mutex protecting the queue and allowing the producer thread to add data. Another application is in thread pools, where a group of threads waits for tasks to be executed. A condition variable can be used to signal worker threads that a new task is available in the task queue. When a task is added, the main thread signals the condition variable, waking up an idle worker thread to execute the task. Beyond these examples, condition variables find applications in various domains, such as event handling. Threads can wait on a condition variable to be signaled when a specific event occurs. such as a button press or a network message arrival. They are also useful for state synchronization. Threads can use condition variables to synchronize their execution based on the state of a shared data structure. For example, a thread might wait for a flag to be set to a specific value before proceeding. By providing this flexible and powerful signaling mechanism, condition variables enable developers to build highly concurrent and responsive systems where threads can efficiently synchronize their actions based on specific events and notifications. Section 4. The power of predicates refining condition synchronization. While condition variables provide a powerful mechanism for event-based synchronization, they sometimes require an extra layer of refinement to ensure that threads wake up only when a specific condition is met, not just when a signal is received. This is where predicates come into play, acting as gatekeepers to ensure that threads awaken only when the time is right. A predicate, in the context of condition variables, is a Boolean expression that evaluates the desired condition. Instead of blindly waking up all waiting threads upon receiving a signal, the predicate acts as a filter, ensuring that only threads for which the condition holds true are awakened. This selective awakening is crucial for preventing spurious wake-ups, situations where a thread wakes up only to find that the condition it was waiting for is no longer true. Spurious wake-ups can lead to subtle and hard-to-debug errors, as threads might make decisions based on outdated or invalid information. Consider a scenario where multiple consumer threads are waiting for data in a queue. Without predicates, if a producer thread adds data and signals the condition variable, all waiting consumer threads might wake up, even though only one can acquire the mutex and retrieve the data. This leads to unnecessary context switches and potential performance degradation. By associating a predicate with the condition variable, we can ensure that only consumer threads waiting for the specific type of data added by the producer are awakened. For example, the predicate could check if the data type matches the consumer's requirement. By incorporating predicates into condition variable synchronization, developers can achieve a higher level of precision and efficiency, ensuring that threads wake up only when the desired condition is met, reducing spurious wake-ups and optimizing system performance. Section 1. The producer-consumer problem, a classic concurrency challenge. In the bustling world of concurrent programming, where multiple threads or processes collaborate to accomplish complex tasks, the producer-consumer problem stands as a classic challenge, a synchronization puzzle that highlights the need for careful coordination. Imagine a factory assembly line where some workers diligently produce items while others just as diligently consume them. The challenge lies in ensuring a smooth flow of goods, preventing shortages and overproduction. The producer-consumer problem, in its essence, involves two types of concurrent entities: producers, which generate data or tasks, and consumers, which process or consume this data. The producers and consumers typically operate at different speeds, and their interaction must be carefully orchestrated to prevent data loss or deadlocks. Imagine a scenario where a producer thread writes data to a shared buffer, while a consumer thread reads and processes this data. If the producer is faster than the consumer, the buffer might overflow, leading to data loss. Conversely, if the consumer is faster, it might end up reading empty buffer slots, resulting in wasted processing time. To address this challenge, we need synchronization mechanisms that allow producers and consumers to communicate their status and coordinate their actions. Semaphores and condition variables, the trusty tools in our concurrency toolkit, provide elegant solutions for tackling the producer-consumer problem, ensuring smooth and efficient data flow between these concurrent entities. As we delve deeper into the solutions, we'll explore how semaphores and condition variables act as orchestrators, preventing data loss, avoiding deadlocks, and ensuring a harmonious balance between production and consumption in our concurrent systems. Section 2. Semaphores as orchestrators, coordinating producers and consumers. Semaphores, with their ability to control access to shared resources, emerge as natural orchestrators in the producer-consumer ballet, ensuring that producers don't overwhelm consumers and consumers don't starve for data. Imagine them as traffic signals at a busy intersection, directing the flow of vehicles to prevent accidents and maintain order. In the producer-consumer scenario, we can employ two semaphores, one to signal the availability of empty slots in the buffer, and another to signal the presence of data in the buffer. The semaphore representing empty slots is initialized to the buffer size, while the semaphore representing filled slots starts at 0. When a producer thread wants to add data to the buffer, it first performs a wait operation on the empty slots semaphore. If there's an empty slot available, the semaphore's counter is decremented, and the producer proceeds to add data. If the buffer is full, meaning the semaphore counter is 0, the producer is blocked until a consumer retrieves data, freeing up a slot. Conversely, when a consumer thread wants to retrieve data, it performs a wait operation on the filled slot semaphore. If data is available, the semaphore's counter is decremented, and the consumer retrieves the data. If the buffer is empty, again meaning the semaphore counter is 0, the consumer is blocked until a producer adds data. This intricate dance of wait and signal operations ensures that producers only add data when there's space and consumers only retrieve data when it's available. Semaphores, in this way, act as the guardians of the shared buffer, preventing both buffer overflows and underflows. By carefully managing the flow of data between producers and consumers, semaphores provide a robust and efficient solution to the producer-consumer problem, ensuring smooth operation and preventing data loss in concurrent environments. Section 3. Condition variables for elegance, streamlining producer-consumer interactions. While semaphores provide a reliable solution to the producer-consumer problem, condition variables offer a more elegant and efficient approach, especially in scenarios where threads might need to wait for specific conditions rather than just resource availability. Think of them as sophisticated waiting rooms where threads can, relax until a particular event or state change occurs. In the producer-consumer context, a condition variable can be used to signal consumer threads that data is available in the buffer, while another condition variable can signal producer threads when there's space to add data. This eliminates the need for separate semaphores to track empty and filled slots, simplifying the synchronization logic. Producers and consumers share a mutex which protects access to the shared buffer. When a producer thread wants to add data, it acquires the mutex and checks if there's space in the buffer. If so, it adds the data and signals the data available condition variable, waking up a waiting consumer thread. If the buffer is full, the producer releases the mutex and waits on the space available condition variable, allowing consumers to retrieve data and free up space. Similarly, when a consumer thread wants to retrieve data, it acquires the mutex and checks if there's data available. If so, it retrieves the data and signals the space available condition variable, potentially waking up a waiting producer thread. If the buffer is empty, the consumer releases the mutex and waits on the data available condition variable, allowing producers to add data. This elegant use of condition variables allows for more precise signaling and avoids unnecessary context switches. Threads wait only for the specific conditions they need, making the synchronization mechanism more efficient and responsive. By leveraging the power of condition variables, we can achieve a more streamlined and efficient solution to the producer-consumer problem, ensuring smooth data flow and minimizing unnecessary waiting and resource contention. Section 4. Real-world implications from multimedia streaming to asynchronous task queues. The producer-consumer problem, far from being an abstract concept confined to textbooks, manifests in numerous real-world applications, shaping the way we experience technology and interact with the digital world. From streaming our favorite movies to managing asynchronous tasks in software systems, the solutions we've explored have far-reaching implications. In multimedia streaming, the producer-consumer pattern is the backbone of smooth playback. Video and audio data are continuously produced by a source, like a video server, and consumed by a player, such as your web browser. Buffering mechanisms, often implemented using queues and synchronization primitives, ensure that data is delivered at a consistent rate, preventing stuttering and interruptions, even if the network connection fluctuates. Asynchronous task queues, another common application, rely heavily on the producer-consumer paradigm. Tasks are submitted to a queue by producers, such as users interacting with a web application, and worker threads act as consumers, retrieving and processing these tasks in the background. This allows the main application thread to remain responsive, handling user requests while tasks are processed asynchronously. Other real-world examples include event handling systems, where events are produced by various sources like user input or sensors and consumed by handlers that process these events and trigger appropriate actions. Logging systems are another example, where log messages are produced by different parts of an application and consumed by a logger that writes them to a file or database. And finally, data pipelines, where data is produced by one component, processed by another, and eventually consumed by a destination, often involving multiple stages and transformations. The prevalence of the producer-consumer pattern in these diverse domains highlights its significance in modern software development. Understanding how to effectively solve this concurrency challenge using semaphores and condition variables is crucial for building robust, efficient, and responsive systems that power our digital world. Section 1. Bash concurrency, unleashing parallelism in the shell. The Bash shell, a staple in the world of Linux and Unix-based systems, might seem like a simple command-line interpreter. However, beneath its unassuming exterior lies a powerful engine capable of handling concurrency, allowing users to execute multiple commands or scripts simultaneously and harness the full potential of their multi-core processors. Concurrency in Bash isn't about creating threads or processes in the traditional programming sense. Instead, it leverages the operating system's ability to run multiple programs concurrently, enabling users to launch background processes, chain commands together, and even simulate more advanced synchronization primitives using readily available tools. Imagine you're working on a project that involves processing multiple large files. Instead of running these processes sequentially, which could take hours, you can unleash the power of Bash concurrency to run them in parallel, significantly reducing the overall processing time. While Bash might not offer the sophisticated synchronization mechanisms found in languages like Java or C++, it provides a pragmatic and efficient way to introduce concurrency into shell scripts and command-line tasks. By understanding the tools and techniques at our disposal, we can automate complex workflows, optimize resource utilization, and boost our productivity in the command-line realm. As we delve deeper into the world of Bash concurrency, we'll explore how to launch background processes, manage their execution, and utilize pipes and subshells to chain commands together, creating efficient and powerful workflows right from the command line. Section 2. Background processing, juggling tasks with and wait. Now, one of the simplest, yet most powerful forms of concurrency in Bash is background processing. This is essentially the ability to launch a command or script in the background while continuing to work in the shell without waiting for it to finish. Think of it as juggling multiple tasks at once, keeping everything moving smoothly without being bogged down by individual processes. The magic symbol that makes this possible is the ampersand and. By appending an ampersand to the end of a command, we tell the shell to execute it in the background. This means control is returned to the prompt immediately, even if the command itself takes a long time to complete. For instance, instead of waiting for a time-consuming file compression to finish, you could do this, or you can send it to the background by typing. Now, the shell immediately returns to the prompt, allowing you to continue working while the compression happens in the background. But you might wonder, what if we need to wait for that background process to finish before moving on? Well, that's where the wait command comes into play. By using wait followed by the process ID or PID of the background process, we can pause the shell's execution until that specific process is complete. For example, this combination of background processing and the wait command gives us fine-grained control over concurrent execution in Bash. It lets us launch, monitor, and synchronize processes exactly as needed. Section 3. Pipelines and subshells. Chaining commands for efficiency. Bash offers us another powerful tool for concurrency and efficiency by allowing commands to be chained together using pipes and subshells. This enables us to create complex data processing pipelines and execute multiple commands as if they were a single unit. Pipes, represented by the vertical bar, or act as conduits for data. They redirect the output of one command directly into the input of another. This creates a seamless linear chain where data flows from one stage to the next, much like an assembly line, with each station performing a specific operation. For instance, to list the contents of a directory, filter the results to show only text files, and then count the number of lines in each file, you could write grep. Text $WCL grep, text $WCL here. Each command in the chain works concurrently, processing data as it becomes available from the previous command. This approach not only simplifies the syntax, but also optimizes execution time, as there's no need to write intermediate data to files and read it back in. Now, subshells, on the other hand, are created by enclosing commands in parentheses. This allows us to group multiple commands and execute them as a single unit within a separate shell process. Subshells are particularly useful for isolating side effects, ensuring that variables and environment changes within the subshell don't affect the parent shell. For example, if you need to navigate to a specific directory, perform some operations, and then return to your original directory, you could use a subshell like this. By combining pipes and subshells, we gain the ability to build powerful and efficient command line workflows. This allows us to chain commands together to process data, manipulate files, and automate complex tasks with remarkable conciseness and flexibility. Simulating semaphores in Bash, well, it's a fascinating topic. While Bash might not have native semaphores like some higher-level programming languages, its flexibility and access to system utilities allow us to simulate their behavior with, honestly, remarkable accuracy. This opens up a whole new world of possibilities for managing concurrency in shell scripts. It lets us tackle more complex synchronization challenges, all without stepping outside the comfort of our command line environment. Now, the key to simulating semaphores in Bash lies in leveraging atomic file operations. These guarantee that operations on a file are performed as a single, indivisible unit, even when multiple processes are trying to access the file at the same time. By treating files as our semaphore counters and using atomic operations to manipulate them, we can mimic the classic wait and signal operations, the very heart of semaphore-based synchronization. Picture this: multiple Bash scripts need to coordinate access to a shared resource like a log file or maybe a database connection. By implementing a simple semaphore mechanism using atomic file operations, we can ensure that only one script accesses the resource at a time. This prevents conflicts and, of course, maintains data integrity. Now, I'll admit this approach might not be as fast as using native semaphores in a compiled language, but it's practical, accessible, and a solid way to introduce semaphore-like synchronization into your Bash scripts. It allows you to manage concurrency with greater control and reliability. And as we dig deeper, we'll also explore how to use the SEM command, an incredibly handy utility designed specifically for simulating semaphores. It simplifies synchronization tasks and helps us build more robust and reliable concurrent scripts. When working with concurrency in Bash, you're often juggling multiple processes, coordinating their access to shared resources, and trying to ensure that everything runs smoothly. No race conditions, no deadlocks. It can be, well, a bit overwhelming, but thankfully the SEM command is here to help. It's a valuable ally in this endeavor, providing a straightforward way to simulate semaphores and introduce robust synchronization into your shell scripts. Now, the SEM command, which is often part of the GNU parallel suite of utilities, might seem unassuming at first glance, but its ability to acquire and release named semaphores with atomic precision makes it a powerful tool for managing concurrent processes in Bash. Think of it as a virtual traffic light. It ensures that only a limited number of processes can proceed at a time, preventing chaos and maintaining order in your scripts. Take this example. Imagine multiple instances of a Bash script need to update a shared counter stored in a file. Without proper synchronization, these concurrent updates could result in incorrect data because multiple processes might try to read and write to the file at the same time. The sem command provides an elegant solution. By associating a named semaphore with the file, you can ensure that only one process acquires the semaphore at a time. This effectively serializes access to the counter and prevents race conditions. Once a process finishes updating the counter, it releases the semaphore, allowing other waiting processes to acquire it and proceed. This simple yet powerful mechanism, made possible by the sem command, lets us introduce semaphore-like synchronization into Bash scripts. It enables us to control concurrency, prevent race conditions, and build more reliable and robust concurrent applications. Alright, let's bring all this theory into practice. We'll build a simple yet illustrative Bash script that uses the sem command to synchronize access to a shared resource. This will really show you the power and practicality of this approach. Imagine a scenario where multiple instances of a script need to write to a shared log file. To prevent interleaved output and ensure each message is written atomically, we can use a semaphore to control access to the file. Here's a basic example of such a script. First, we define a variable to store the path to the shared log file, and A for our semaphore. The and functions encapsulate the logic for acquiring and releasing the semaphore using the command. The function acquires the semaphore before writing a timestamp message to the log file, then releases it afterward. If you run multiple instances of this script concurrently, you'll notice that the log messages are written to the file in order. No interleaving, no chaos. It's a simple demonstration, but it clearly shows the effectiveness of semaphore-based synchronization. This example highlights how the sem command can be used to introduce robust synchronization into Bash scripts. It's a practical way to build more reliable and predictable concurrent applications. As we've journeyed through the intricate world of concurrency, we've explored the challenges and triumphs of making programs do multiple things at once. And, well, we've seen just how crucial synchronization is for bringing order to this potential chaos. Think of it like a conductor guiding a symphony orchestra. Synchronization ensures that each instrument plays its part harmoniously, creating a beautiful and cohesive performance. We've delved into the perils of race conditions, where unpredictable thread timing can lead to unexpected results, and the crippling embrace of deadlocks, where processes become stuck in a perpetual standstill. Synchronization is the key to avoiding these pitfalls and building robust, reliable concurrent systems. Semaphores, with their elegant counter-based approach, have proven to be powerful tools for managing access to shared resources. They prevent conflicts and ensure that processes cooperate without stepping on each other's toes. We've explored binary semaphores, acting as simple on-off switches, and counting semaphores, which manage access to pools of resources. Condition variables, on the other hand, have provided a more sophisticated mechanism for synchronizing based on specific events or state changes. Through practical examples, we've seen how these synchronization primitives can solve classic concurrency challenges like the producer-consumer problem. And we've even extended this knowledge to the command line realm, simulating semaphore-like behavior in Bash. Mastering these advanced synchronization techniques isn't just an academic exercise, it's a crucial skill for any developer working in the world of concurrency. As multi-core processors become the norm and the demand for responsive, efficient software grows, the ability to write well-synchronized concurrent programs will be absolutely essential.